So this video is going to cover how to determine molecular geometry. And we're going to go through the basic steps, and we'll go through some examples, but we're not going to cover every possible molecular geometry because that would just take too long. So first, the first step in determining molecular geometry is to draw the Lewis structure. And if you're unsure of anything about how to draw Lewis structures, be sure to review that first, because that's the first step, and you absolutely have to get that right to determine the geometry correctly. From the Lewis structure, what we want to do next is count the groups of electrons around the central atom. And remember, a group of electrons can be a single bond, or a double bond, or an unshared pair of electrons. It doesn't matter. Each one of those counts as one group of electrons. And then once we know how many groups of electrons we have, what we want to do is arrange those groups of electrons around the central atom so that the repulsion between them is minimized. All of those electrons carry a negative charge, and like charges repel, so we have to get those groups of electrons as far apart as possible. And then once we've got the groups of electrons as far apart as possible, and we know how they're arranged, what we want to do then is add the exterior atoms back onto the molecule, and in some molecules it might be possible to put those atoms back on in more than one way, and we'll look at how to deal with those when they come up. So those four steps: draw the Lewis structure, count the groups of electrons, get those groups of electrons as far apart as possible, and then add the atoms back on to determine geometry. So we'll start with these three examples. BeH2, the SO3 2- anion, and the ClO4- anion. And we'll take BeH2 first. There's the Lewis structure for beryllium hydride. Remember, beryllium's small. It doesn't have to complete its octet, so it's only got two groups of electrons around the central atom, and that looks something like that. Those two groups of electrons are in a linear arrangement around the central beryllium atom. And now that we've got those two groups of electrons on, we'll put the exterior atoms back on. We add the two hydrogens. Now it looks like that, and we see that the molecule is still linear. So that's got a molecular geometry that's linear. And keep in mind, there's a distinction between electron geometry and molecular geometry. When we look at electron geometry, we're just talking about groups of electrons. And when we talk about molecular geometry, we're worried about how all of the atoms are connected. So there's beryllium hydride. Lewis structure, groups of electrons, add the exterior atoms, determine the geometry. So SO3 2-. There's its Lewis structure, SO3 2-, and it's got four groups of electrons. Two single bonds, an unshared pair, and a double bond. And each one of those counts as a group of electrons. So when we put those groups of electrons around the central sulfur atom, it would look something like that, and those four groups of electrons are in a tetrahedral arrangement. So four groups of electrons, tetrahedral arrangement, and now we need to put the exterior atoms back on. But we've only got three exterior atoms, and in SO3 2-, it doesn't matter where we put them, we'll arrive at the same geometry either way. So we put the three exterior atoms back on, and we ignore the unshared pair when we talk about molecular geometry. So those unshared pairs help determine the molecular geometry, but we're not going to consider them when we actually describe the geometry of the molecule. So there's what SO3 2- looks like, and its molecular geometry is trigonal pyramidal. So there's SO3 2-, four groups of electrons, three atoms attached, trigonal pyramidal geometry. ClO4 2- has that Lewis structure. It's got four groups of electrons, so just like SO3 2-, those four groups of electrons will be arranged exactly the same, and we still have the tetrahedral arrangement. Now we've got four exterior atoms to put back on. We add the four oxygens back on, it looks like that, and that molecular geometry is still tetrahedral. Right? So if you look at these two examples, right, in ClO4-, which doesn't have an unshared pair of electrons. The electron geometry and molecular geometry are the same. But in SO3 2-, where we have unshared pairs of electrons, the electron geometry and molecular geometry are different. So make sure, as you work through problems, that you keep that distinction in mind. Now, let's look at a couple more, slightly more complicated examples. SF4 and BrF3. So SF4 has that Lewis structure. We have 4 fluorine atoms and 1 unshared pair of electrons. So we've got 5 groups of electrons around the sulfur, which gives us an electron geometry that looks like that. And that electron geometry we refer to as trigonal bipyramidal, sort of 2 pyramids with a 3-sided base, right? That's where the trigonal bipyramidal comes from. So now there's a question about where to put the unshared pair. We could put the unshared pair in either this equatorial position, or we could put it in this axial position. And that decision is based on minimizing repulsions. So if we put the unshared pair of electrons in this equatorial position, that unshared pair of electrons is only at 90 degrees to 2 bonded atoms, right? We have 2 90-degree repulsions between the unshared pair and the bonded atoms. But if we were to place it in this axial position, now it would be at 90 degrees to 3 groups of electrons, right? We'd have an extra 90-degree repulsion, which is why that unshared pair of electrons is in that axial position, right? That minimizes the repulsion. And when we put it in that equatorial position, now we give it a geometry that we call a seesaw molecular geometry. So 4 groups of electrons in an unshared pair will look like a seesaw. And then BrF3, we'll tackle that next. BrF3 has that Lewis structure, 3 bonded atoms and 2 unshared pairs, and that gives us 5 groups of electrons, which has exactly the same electron geometry as SF4, so it's still trigonal bipyramidal. Now we need to put those 2 unshared pairs back on, and those unshared pairs will be in an axial position again. So when we describe the molecular geometry, we get rid of the unshared pairs, and that molecular geometry we describe as T-shaped. So there you are, the basic steps for determining molecular geometry and some examples. Keep in mind, it's all about minimizing repulsions and drawing correct Lewis structures.